In this video, I will tell you what are the applications or what is the meaning of doing a surface integral, okay? Because so far I've just shown you how to do it, but I haven't explained what it means. So basically, the applications of surface integrals are the same as for double integrals, but on a curved surface. And I could leave it there, but let me be more explicit. So for example, you can calculate an area of a surface. So the area of a surface is given by the surface integral along the surface S of ds, the differential of surface. Okay, so this is the same as integrating a function equal to 1. Okay, so this is the same as we could do with double integrals, but now we can calculate surfaces of curved things like the outer surface of a sphere, the surface of a cone, and so on. Yeah, so now you can calculate any surface whatsoever as long as you can write it mathematically. That's great. What else can you do? You can calculate the mass of any surface. Of any surface object. Yeah. So for example, you have some metal plate that is curved, something like that. Okay, and then it turns out that the thickness of this plate is thicker at some points than at others. Okay, so maybe it's heavier here, but a bit lighter here. So you want to calculate the total mass. So you know that the density of this plate changes with respect to the two variables, u and v. So u and v are, remember, the two parameters that you can use to move through the surface. So maybe your density depends on the position, right? So then the total mass is simply given by the double integral on the surface S of the density times ds. Okay? And remember, as usual, that ds has units of length squared, and the density, this would be a density per unit area. It would be a surface density, so this would be in kilograms per meter squared, such that the result is in kilograms. Okay? So you can calculate the mass of a plate, of a curved plate. You can also calculate things like the center of mass. And this is done in the same way that we did for two-dimensional integrals in planar regions. So the vector position of the center of mass is equal to the double integral or the surface integral of the position vector r times the density rho times ds divided by the total mass, which is the surface integral of rho ds. And this is integrated over the surface S. Okay, so identical equation to the other case of double integrals. And you can also calculate, for example, the average of a quantity over a surface. And to explain this, what I mean by this, I have this example here. So let's say that you have the mean temperature at each point on the Earth. Yeah, so of course the Earth is a sphere, and you have your sphere here with your two coordinates that span the sphere. So different points along the sphere have different temperatures. Yeah, the equator is hotter and so on. So what is the average temperature on the surface? You need to calculate an average, and the way you would do that is by doing a double integral. So temperature average would be the double integral over the surface of the sphere of the temperature as a function of the latitude and the longitude, which are the two parameters, theta and phi, times ds, divided by the total surface ds, which would be equal to 4 pi r squared. Okay, so that's how you would calculate the average quantity for some quantity on a surface. So you can see that this is identical to the applications of double integrals, but now we can do them on curved surfaces. So see you in the next video.